So this is just a concept. This is just explain what is the nature of moment of inertia. So moment of inertia is the average squares of radial distance. Remember the dimension of I is equal to mass times distance here. Okay, away from z-axis all the mass elements making up the rigid body. Okay, so you can understand why it has to be L squared. For example, if this is a dependence was linear, okay, then for a symmetric object like this, if this was linear, then you always suppose it has rotational symmetry. For a mass point, you must always have mass point and minus at mirror imaging. Okay, so if I was changing like this, then it should be always zero for a symmetric object. Okay, so but we know that this is not true because it has moment of inertia. You need some external torque to rotate this thing, so it has to go like ml squared. Okay, so the gyro radius of gyration is defined to be I is equal to mk squared on the average. This is average mass squared. So for example, if I have a so here here the radius gyration is defined to be mk squared. Okay, so that is average kind of distribution of mass at this point here. Okay, so that is the definition of radius of gyration. So let me just give an example here. Radius of gyration is thin rod passing through one end. So suppose you have thin rod passing through one end here. We know that is 1/2, 1/3 ml squared, which is defined to be mk squared. K is radius gyration, and radius gyration is like a over root 3. So radius gyration is a over root 3, which is about this. Okay, root 3 is what? 1.6. So 0.8. So maybe around here. Okay. So what this one tells you is that when this as far as rotation is concerned, this thin rod behaves as if all the mass is concentrated at here. It is uh, greater than less than 1 L. Here, so center of mass is here. Sorry, so it is around here like this. Okay, because this square root 3 is what? 1/6 or something, 1/7 or something. Okay, so radius gyration is here. So anyhow, the radius gyration tells you as if that this is a distance, as if all this effect can be summarized as located on that radius. Now let's go to some physical problem here. So you have here, this one is familiar from general physics. So the pivot point is at some point here, and the center of mass is here. So the distance is L. Okay, and it is performing a oscillation around here because the torque is provided by this gravitation. Okay, and if this is theta, then the force is mgl sine theta. Of course, this is equilibrium point, and this is restoring force, so you must have minus sign here, and you have m. So the torque is what? Torque is mgl sine theta. So you have I theta double dot is equal to minus mgl. Okay, so theta double dot is equal to plus I over mgl sine theta is equal to 0. And for small oscillation, sine theta is equal to theta. So therefore, we have theta double dot plus mgl over I theta is equal to 0. Okay. So we know that the general solution is given by this one, where theta 0 is amplitude, and cosine, we can also use the sine times omega t, where here it is expressed as 2 pi f0 t minus some delta for general boundary conditions. Okay. So theta 0 is the amplitude, delta is just phase angle. We know that theta, just remind you that theta 0 and delta is determined in terms of the initial condition theta 0 and theta 0 dot. Okay, and this one is omega squared, so omega is equal to mgl over I. Therefore, f is equal to 1 over 2 pi square root mgl over I. Okay, and the period is obvious, of course, is given by 1 over f0, which is 2 pi square root I, the inverse of this. So that is the case when theta is small. So this is small angle oscillation. And if you write it as a radius of gyration, okay, so what was t0? So let's I don't think we need blackboard here. So you have t0 is equal to 2 pi, what was it? I over mgl. So introducing the radius gyration, as was explained, you have 2 pi square root m cancels, so k squared over gl. Okay, so that is this one. So the period is the same as the simple pendulum of length k squared over l. Okay, remember the simple pendulum was 2 pi square root g over l. Therefore, the length here is this one. Effective length is this one, k squared over l. So if the uniform load, if this is uniform load, and the pivot point is at the end, we know that the I is equal to a squared over 3 times m. Okay, so k squared is a squared over 3, and L is a over 2, is the center of mass, and then the period is t0 is equal to 2 pi 2a over 3g, which is the same as the simple pendulum of length 3 over 2a. Okay, g L over g, L is equal to 2a over 3. Now, let's talk about center of oscillations. So in the text it is defined as follows. Okay, we know that I, using Penarek theorem, is given by I center of mass plus ml squared. Okay, where L is this distance here. So if this is pivot point, this one is L in this case, and center of mass and plus the moment of inertia of this point is center of mass plus distance. Okay, center of mass is always the smallest moment of inertia. Okay, so you have mk square is equal to mk center of mass plus ml square. Okay, so if you cancel just the m's, you have this one. Okay, so T0, which was equal to 2 pi square root mgl over I now is equal to what? 2 pi square root I, m cancels, so this one is equal to mk center of mass squared plus ml squared. So m cancels and it gives you k center of mass squared plus l squared over gl. Okay, so this is T0. Okay, suppose that the axis of rotation of physical pendulum is shifted to a different position. So originally, in the original case, this one was center of mass, so this one was L. Suppose it is shifted to the other side, L prime. Okay, so suppose now it is performing a small oscillation around L prime. Okay, then of course the period from this consideration here just gives you k center of mass plus L prime square, because it's now doing, so you can just think of this as a here this one center of mass, this is L prime, and the original L, this one is L. Now it is performing a small angle oscillation with distance between the central mass and the pivot point is L prime. Then of course it will give you this one. Okay, so T0 for original pivot point gives you L square, this one is common, and T0 prime now gives you L prime. Okay, so if and then one can ask, what is the period of oscillation when they are equal? So it just you have to remember this one is k center of mass square plus L square, which is equal to square root L prime k center of mass square plus L prime square. Okay, if you square it, then you have L prime k center of mass plus L square L prime should equal to L k center of mass squared plus L prime squared. Okay, now if I correct k center of mass here, then you have L k, sorry, this one should be squared, k center of mass squared. Let's just push this into here. If you have L prime minus L, it should equal to, moving this into the right hand side, you have L prime squared minus L squared L prime, which gives you L prime minus L. Okay, so these things can cancel. Therefore, the condition that that this period is equal for the other point is what? L prime is equal to k center of mass square. Okay, so that is the condition that the periods are equal. The point O prime, remember the point O prime is located, given a point O, you have center of mass, you have the other point here, okay, the O prime, which is L prime and L. So when they are equal, this O prime is called the center of oscillation for the point of O. Conversely, O is the center of oscillation for O prime. Okay. So, for example, for a load of length A swinging about 1n, we know that K center of mass square is 1/12. Okay, I think everybody now is familiar. I mean, know by heart that the moment of inertia for this load with the length A is 12 ma squared. Okay, and L is equal to A over 2. Then if you use this one, it just gives you L prime is A over 6. Okay, so let's magnify this. So this one is A over 2, and if it is rotating about this center of oscillation for O, its distance is A over 6. So oscillation about this axis, oscillation about this axis gives you the same period. Okay. Now let's magnify this. The letter is so much smaller. Oops, it's almost the same. I think we have to go with this. Now, here you are considering a large oscillation. Okay, so the theta is no longer very small oscillation, but it's large. Okay, so this theta, for example, the initial theta 0 is no longer can be very large here. It's no longer small relation, no longer a small oscillation. So let's approach this problem, and in this case it is very convenient to use the energy conservation. Okay, so here what is written is that kinetic energy plus potential energy is equal to total energy. Okay, so if this is theta 0, let's call this length L, and we take this point to be potential to be 0, then the initial total energy is which is at this point, suppose at arbitrary theta 0 it is starting, then is obviously given by this one was L cosine theta. This is theta. Therefore, the initial energy, the H, is equal to what? H is equal to L minus L cosine theta, which is equal to L 1 minus cosine theta, 0. Okay, so kinetic energy is 1/2 I omega squared, and which is equal to I 1/2 I theta dot squared plus the potential energy is mgl 1 minus cosine theta at arbitrary, when it has moved to arbitrary theta. That add up should equal to mgl 1 minus cosine theta 0, which is the original energy. And we are considering the case where theta 0 is no longer small. Okay, so you have here this equation, 1/2 I theta dot squared plus mgl 1 minus cosine theta is equal to mgl 1 minus cosine theta 0. And we are familiar from the general physics or from the first semester that this one, to solve this one, you can just use this to find the equation first order. So this one is first order equation. That is one of the convenient thing convenient step when you take this energy conservation. Okay, so since this each step is rather easy, I'll just go through this. Okay, so here now you have integral here dt. If you put this into here, you have d theta over 2 mgl over I square root, okay, times cosine theta minus cosine theta 0 1/2. Okay, so just this one, just put into the numerator. You have square root I over 2 mgl d theta over cosine theta minus cosine theta 0. Okay, 1/2. So that is this result. So our main concern is how the period changes compared to the small oscillation. Okay, so here the period should be given by 4 times. From this one is from 0 to theta 0. Okay, so the period that is make one complete swing should be equal to 1, 2, 3, 4. So if you integrate from 0 to theta 0, the period will be 1, 2, 3, 4. So you should have factor 4 here. Okay, you must have factor 4. Okay, so t is equal to 4 times square root I over 2 mgl times 0 to theta 0 d theta cosine theta minus cosine theta 0 over 1/2. Okay, so that is the period. Okay, so this integral can be manipulated into very well-known integrals, so-called elliptic integrals. Okay, so in the special function, we will have the opportunity to encounter this function. So let me just go through this manipulation to put into the standard form of the elliptic integral. Okay, so you just have to follow the steps that is described in the text. It's not difficult one. Okay, so here to go to elliptic, to express this in terms of elliptic integrals, you introduce a sine phi, which is equal to sine theta over 2 over sine theta 0 over 2, and let's write it as 1 over k sine theta over 2. Okay, so k is equal to sine theta 0 over 2. Okay, then here the boundary condition is when theta is equal to theta 0. So just pay attention to this expression. When theta is equal to theta 0, sine phi over 2 it should be 1. Therefore phi sine phi, not just sine phi, not phi over 2, sine phi. So phi should equal to pi over 2. Okay, and when theta is equal to 0, of course the phi should equal to 0 because sine phi is equal to 1. Okay, so you have these boundary conditions, and then use this form here. cosine theta we know is 1 minus 2 sine square theta over 2. Okay, and of course cosine theta 0 is equal to 1 minus 2 sine square theta 0 over 2. Okay, therefore you have square root cosine theta minus cosine theta 0 should equal to square root 2. Okay, 1 cancels. Okay, then sine square theta 0 over 2 minus sine square theta over 2. Okay, and that can be written as square root 2. If I just factor it out, sine theta over 2, then you have 1 minus what? Sine square theta over 2 over sine square theta over 2. So it should be sine square phi. Okay, so the factor here is 2 sine square theta over 2, 1 minus sine square phi. Okay, so let me just go through this. And then you need integral here. Okay, take care of this d theta here. So you have from here, okay, cosine phi, if we take differentials of this, that should equal to here sine theta 0 over 2 over here what? Cosine theta over 2 times 1/2 times d theta. Therefore, d theta, which is necessary here, is what? Therefore, d theta should equal to 2 here, 2 and sine square theta over 2. So you have 2 cosine phi and sine theta square over 0 over 2 times d phi. Okay, over here cosine theta over 2. Okay, so that is just elementary consideration. Okay, so let's erase now here. So put everything into here. So the result was that d theta, we have calculated d theta is equal to 2 cosine phi sine theta over 2 d phi over cosine theta over 2. Okay, so just put this in here. Okay, and it gives you this. Let's just write down this. This one is 4 times this one is there, and the integrand gives you what? D theta, which is 2 cosine phi sine theta 0 over 2 d phi over cosine theta over 2 times what was the cosine and here you have cosine theta minus cosine theta 0, which is equal to what? Square root was square root 2 was square root 2, sorry, square root 2 sine theta 0 over 2 here in the denominator, and it was 1 minus sine square phi Okay, so this cancels. You have square root here, sorry. This cancels. So you have here d phi here d phi over cosine theta over 2, which is equal to what? Cosine theta over 2 is what? Square root 1 minus k squared sine square phi. Okay, so cosine theta over 2, which is equal to square root 1 minus sine square theta over 2, and sine square theta over 2 is sine square theta 0 over 2 times sine phi. So you get this one. Okay, so putting this all numerical, so that is from 0 to pi over 2 is elliptic integral. So it took us for some time, but anyhow, here this one 1 minus k square sine square phi. Okay, and that is the elliptic integral. So obviously I cannot I can do it. Okay, so this one, okay, so that is the elliptic integral. This factor we have just derived here. So this one is integral over pi over 2 that was explained. In general, the elliptic integral is 1 minus k squared sine square pi from 0 to pi. Okay, so that is the elliptic integral of first kind. Okay, so our period for this is this one, fk over 2. Okay, remember k is equal to sine theta 0 over 2, so it is the amplitude. Okay, it's the amplitude. So when theta 0 is small oscillation, it is the same as t0, which was equal to 2 pi square root I over mgl, if I remember correctly. Okay, so that is t0. Now as the initial theta 0, where this rotation starts, becomes bigger, larger, then the period begin to deviate from t0, and it increases as it should. Okay, so when theta is equal to 135 degrees, for example, so how much is it? 135 means around here, so this is 45. So you just drop the rigid body here. It starts like this, and then the period is 1.1804 t0. Okay, so here, sorry, yeah, 1.5281 t0. And if this is the amplitude is infinity, so this can be understood physically. Okay, so you just give a very small, either in this direction or in this direction, rotate it. Suppose this is pivot point here, then it will just rotate and just come back here. Okay, and you just stop here. So the period is infinity in this sense. It takes infinite time. Comes here, and actually if you calculate it, it takes here it starts quickly, but it actually takes infinite time to reach at this point here. Okay, so the period in this case is infinity. Just make two comments. Actually, one is comments and the other is this example. So my first comment is that when we calculated t, I'm talking about some factor here. Okay, so you have I over 2 mgl 0 to theta d theta over cosine theta minus cosine theta 0. Okay, and here you I'll only talk about factors. Here you have square root of 2, and d theta had factor of 2 because d theta is 2 times cosine blah blah blah. Okay, so you have 2 here, and this one was square root 2 1 minus sine square theta over 2, so you have square root factor of 2, so this cancels. Okay, so this finally goes into just I, the t was equal to 4. Okay, you have here half, 1/4, 1/4, 1/4, so 4 times mgl. This two fact this and this all cancels. Okay, and then it's given by 0 to pi over 2 d phi over square root 1 minus k squared sine squared phi. Okay, so this vector we derived, and this vector cancels, and the answer is this one. Okay, so that is the first comment. And the second one, let's go to the example here. Okay, so simple pendulum is given, and it gives a sudden blow at the bottom that this then will of course swing up, and the total energy is given by 2 mgl. Okay, where m is the mass of the pendulum and l is the distance of its central mass to pivot point. Okay, so this is a large angle oscillation, and we can just go through this. The energy equation is 1/2 I theta dot squared plus mgl 1 minus cosine theta. Okay, k plus potential energy, kinetic potential, is now 2 mgl. So you can write it as theta dot. So this one for this particular total energy, this solution is analytic. Okay, so this one is in general is not analytic. It's numerical values can be given, but this one for this particular total energy is analytic, and that's what is this example is about. Okay, so you have theta square dot is equal to 2 mgl over I, and here you have, if you put this in here, mgl cancels, so you have 1 plus cosine theta. Okay, which is equal to 4 mgl over I, and this one is 2 cosine squared theta over 2, so it's cosine squared theta over 2. Okay, so this equation can be solved analytically by introducing a new variable y, which is equal to sine theta over 2, and then this equation is just elementary, so let me just go through this. So y dot is equal to 1/2 cosine theta over 2 over theta dot. Okay, Because if you differentiate y dot, you have one factor, 1/2, and then this one becomes cosine theta over 2, and that cancels one of the cosine theta over 2. And that is equal to what? 1/2 1 minus y squared 1/2 times theta dot. Y dot is this one, and then this equation now can be written as theta dot is equal to 2 y dot over square root 1 minus y squared, and then this one can be written as 2 mgl, so mgl over y 1/2 mgl over y 1/2 1 minus y squared 1/2. So just from this equation, by changing the variables, you arrive at this this equation. Okay, so 2 cancels. So it becomes y dot is equal to mgl over I 1/2 times 1 minus y squared. Okay, and the solution of this equation is very simple. It's called tangent type. Square root mgl over I times t. So everybody knows what the tangent type looks like. There's some amplitude here, and it goes like this. Okay, so that is tangent type. So here you see as t goes to infinity, y goes to 1. Y equal 1 means theta is equal to pi. Okay, that was the infinity. Theta equal pi is this one. This one is theta, so theta equal pi is at the top. Okay, so that is just upside down. So you see, I told you that it takes infinite time to reach. You just start from here and make one complete revolution. It takes infinite time here. So this region is this region here. So it takes infinite time to reach this one is theta is equal to pi. Okay, so it starts from theta is equal to minus pi. Okay, and then turns upside down, and then it takes infinite time. Okay, so this one for this particular energy is a good example to show that this it takes infinite time from theta is equal to minus pi to theta is equal to pi. Okay, so in this parameterization, the equation, this elliptic integral of first kind, it has an exact solution. Okay, okay, so now let's go to Riemann motion. Okay, so let's enlarge this a bit. So what is the laminar motion? So laminar motion, so literally laminar is stratified. Okay, it's like stream line here. Okay, so in rigid body, laminar motion means that if you have plane and all the particle moves parallel to this one. Okay, so you have plane from this side and all the particle moves from this direction. It could rotate and but the motion is all parallel. Okay, so in this side also, if you look at this, then it's all parallel. Okay, so typical example is just a planar object rotating about g-axis, and then all the point moves parallel to this, or this could extend. Still, if you consider a rotation, for example, about center of mass, then all the particle will move parallel to this plane, xy plane. Okay. Sometimes this axis, because if you have a plane, you can always consider an axis here, which is perpendicular. It means that all the particle moves perpendicular to this axis. But this axis itself can move parallel. The direction is fixed. Okay, direction is fixed, but it can parallel transport itself. So the typical example is this disk rolling down the inclined plane, and it's rotating around this center of mass or this point here. But for example, if you consider center of mass, then the axis here is not fixed. The direction is always points in the same direction, but this axis is not fixed. Okay, so that is also a laminar motion, because all the particle is always moving around direction perpendicular to this axis here, axis of rotation. Okay, so that is the definition of laminar motion. And in here, the issue is that if you consider a laminar motion about this point, okay, so suppose that the O point is inertial frame here, dt over dl is given by n. Okay, so that is the standard torque equation. And suppose you have here another point here, but O prime is not fixed. It's going a translational motion. It could be accelerating or something like that. Then with respect to this reference frame O prime, can you use also dt over dl prime is equal to n prime? Okay, so this equation is with respect to a arbitrary point. Okay, this could be center of mass, for example, center of mass accelerating, things like that. So can I still use this equation? A prime is the angular momentum with respect to O prime, and n prime is torque with respect to O prime. Okay, so does this still holds? Here, for the outside reference frame, we know that this holds because this is standard torque equation. So we want to find the condition that we can still use this one and apply it to a laminar motion. Okay, so the analysis starts with this equation, which is standard one, and we know that L is given by R cross MV. L, i's point is equal to Ri times MPi, which is equal to Ri cross MVi. Okay, so that is, this is the equation. dt over dl is this one. Okay, so now I consider an arbitrary point. Okay, it doesn't have to be center of mass. It's just arbitrary reference frame which is moving, for example, or accelerating even. Okay, then we want to check whether this equation is still true. So here, if I calculate this quantity, then n prime obviously is going to be I Ri cross Fi. Okay, and then this equation that we are going to put, since this is true always, we are going to use exploit this equation. So I think we can make it a little bit smaller now. Maybe 120. Okay, so what you do is you first calculate torque with respect to n. Okay, so let's just remind you what was this one. Was O, this one was O prime. Okay, and that is coordinate with respect to O prime, and this one is coordinate with respect to this is ice point particle, and that is R0, I think. Okay, so with respect to O prime, you have Ri cross plus F prime, and here of course Ri is equal to R0 plus Ri prime. Okay, so F I is m dt over dp I. The pi is of course m vi, which is m dt over d vi is dt over d v0 plus vi. Okay, so remember v0 is not a constant. It could this point can accelerate. Okay, so and then in the first term you have minus, the cross product, change it to minus v0 times m Ri prime, and the second one was Ri prime times dt over dmi prime. Okay, and this one is minus v0 0 cross miri. It just goes down, and you have here dt over d Ri prime cross mi prime. Of course, you have extra term here, which is, since this differentiation is only acting on vi, you have here also dt over d Ri prime, but this one is 0. Remember, note this one is vi prime. Okay, so this differentiation can be taken out here. Okay, so n prime is equal to minus this v0 dot is minus r0 prime, so that is acceleration of this this reference frame. So if this is translation, then this is always 0. Okay, times MRI prime plus this one is of course RI prime times MIVI is DT over L. So you have N prime is equal to minus R0 double prime cross MIRI prime plus DT over DL prime. Okay, so if this term, I'm sorry, minus, if this term is equal to 0, then you can also use in this frame, in this arbitrary moving frame, you can also use N prime is equal to DL prime over DT. Okay, so this one also holds in O prime frame if this one is 0. Okay, so either this one vanishes separately or the cross product should vanish here. So the best way of the easiest case you can consider is when R0 double prime is equal to 0, then this one holds. Okay, so for example, if the center of mass, suppose this is center of mass, okay, and then if this center of mass is moving with constant velocity, then still you can use this one. Or if the most common case is like this, the example we considered, okay, if this point is fixed, then you can also, this one is also true, because this point, the R double 0 double dot is equal to 0. Okay? So let's see in which case this term vanishes, so that you can still use this torque equation safely. Okay. So the acceleration, there are 3 cases that are mentioned in the text, and the acceleration of rotation vanishes. Okay, so in figure 3.8.52a, you have this case here. Okay? So this point is fixed, O prime is fixed, and then this one is true. And the second one is that the point of O prime that we are considering is the center of mass system or particle that make up rigid bodies. Okay, then this term vanishes because remember this one is R0 double prime, sorry, cross sigma I MIRI prime, and if this point O prime is center of mass, then we know that by definition this one is equal to 0. Okay, so that is the second case here. By definition, if this O prime is center of mass, okay, so it doesn't matter whether the center of mass is accelerating or rotating or whatever. When you set up equation of motion for this point and calculate L prime, and that it will always give you, satisfy this relation, that you calculate angular momentum with respect to this point and then differentiate with time, it will always give you torque around this point. Okay, so that is the second case. The third one is the following. The third one is, for example, this and this does not vanish identically, but cross product vanishes. The cross product vanishes means what? R0 double prime is parallel or anti-parallel to MIRI prime. Okay, so the most illustrative example is a disk rolling down through an inclined plane. Okay, so here, for example, if you consider center of mass, then it doesn't matter, it always true. But suppose you the point is O prime here. Okay, then we know that if this disk roll down, okay, then this point is instantaneous in contact with this inclined slope, and this point moves like this, so this is undergoing a circular motion. Therefore, r0 is in this direction, that is r0 double dot. Okay, the acceleration is centripetal acceleration. But this one, by definition, is also since this one is definition of central mass, will also point in this direction. So therefore they are parallel. Okay. So this laminar motion, this was laminar motion because the axis, the rotation axis, is always coming is coming out of the board. Okay, always coming out of the board. Okay, so maybe I can just draw this direction, in this direction, axis of rotation, and all the particles move perpendicular. So this is laminar motion, but also this one you can also, if you calculate everything in terms of this with this point of rotation, then still you can use this equation dt over dl prime is equal to n prime, because in this case acceleration is centripetal and MIRI is along the direction of the center of mass. Okay, this is by definition of center of mass. Okay, so it should point from in this direction, and their cross product is equal to 0. Okay, so we have three cases. We have three cases where you can use just dt over dl prime is equal to n prime. Okay, of course the best example of this is when O prime is equal to center of mass, then you can just use this one safely. Okay, no problem, even if the center of mass is accelerating or rotating or doing whatever. Okay, so this term vanishes for this one, where r0 double dot is equal to 0. In his case, center of mass, O prime is at center of mass, so this term is 0. And in this case, r0 double prime cross product becomes a 0. Okay. So here, and center of mass is equal to dt over the center of mass, which is equal to, so you can use this equation. Okay, because this is laminar motion. Okay, so all the point moves in the plane which is with a perpendicular axis here, so you can always write as L is equal to I omega, and omega is in this direction. Okay, omega is in this direction, so you can use this one. So the total equation can be written as I omega dot is equal to N. Of course, the center of mass is just one example of this. And this one, this rolling down an inclined plane, you can also use this equation. Either you can consider the problem. We'll come back to this example. You can consider this motion around this center of mass at the origin, or this also as the axis of rotation. Okay, so with this background, let's now consider an example where body is, let's just say it's a disk is rolling down on an inclined plane. Okay, this is laminar motion. Obviously, I explained it. The axis is always, this axis is out of the page, independent of its position of center of mass. Now, the equation is actually familiar with from general physics. Then in the x direction, m, x of center of mass, is so here is first is a free body diagram. Okay, so you have a inclined plane. So here is the instantaneous frictional force, and of course here is normal force. Okay, and here is mg. And then of course the equation of motion is that mg here, now the coordinate is along this direction, so this one decompose it into heat like this and this. Okay, so this one is mg, this one is what, sine theta, and that is mg cosine theta. Okay, this one is theta. So you can see these things if you just extend this one plus this one is pi over 2, this one and this one is pi over 2, but we know that these angles are the same, so that angle should be the same. So here this is mg cosine theta and this one is mg sine theta. So along x direction you have mx double dot is equal to mg sine theta minus fp, okay, frictional force, and y double dot is my double dot is equal to mg cosine theta minus plus fn, the normal force. Okay, since there is no motion along y direction, you immediately get fn. Fn is equal to mg cosine theta. Okay, now we first consider a motion around this direction, around the center of mass. Okay, so let's calculate the torque here. Okay, the torque is what, so you can use this one, dt over dl is equal to n. So L is equal to I times omega dot, which is equal to what? The torque here, let me just write here. The torque here is around this point here is FPA. Okay, this force does not produce any torque because it is pointing in around O. So the torque about point O is Fp times A. Okay, so that is what is here. Fp times A. Okay, so that is the three equations which solves this problem. Okay. Now, if you consider a motion with no slipping means what? The condition for no sleeping. Okay, it drives me crazy. Anyhow, so the condition, the condition for no sleeping. Let me try this one. Okay, it works. The condition for no sleeping is that the angle and angular here, okay, so it means the v x dot should equal to what? A phi. Okay, so that is the, or omega a phi plus phi 0, for example, or from the initial condition, or a times equals a phi dot. I'm sorry, uh, v is equal to a omega. Okay, so that is the condition for no sleeping. So the condition for no sleeping is x central mass is a phi, and also you have here Fp is equal to frictional force should equal to mu s Fn. Okay, so that is familiar from general physics. So x central mass is equal to a omega. X central mass dot, sorry, the acceleration is a omega dot. So from the torque equation, remember the torque equation was I central mass. We are calculating everything in terms of central mass times omega dot was equal to FPA. Okay, so here I central mass times A, and this one is also X central mass over A, so it has A squared. X central mass is Fp. Therefore, X central mass is equal to mg sine theta minus, this one was Fp. Okay, this is Fp. So gravitational force accelerate. This one is mg sine theta, and this one is Fp. Okay, minus I central mass A square X central mass. Therefore, from here you see, if you push this here, you get acceleration x central mass double dot is equal to, if I put this into here, you have g sine theta over m divided by m both sides. You have m plus I central mass over a squared. Okay, if you put this, divide both sides by m here. I'm sorry, this should be, this doesn't, you see, this doesn't match. Let's do this here. Here you have 1 plus I central mass of a squared times x central mass double dot is equal to mg sine theta. Okay, therefore x central mass double dot should equal to mg sine theta over 1 plus I central mass over a squared. There is, oh, I'm sorry, here you must have m here. Okay, m x double dot is mg sin theta. So sorry, you have here m. Okay, so that cancels m here and here m. So sorry, so many mistakes here. This one should be written as x center of mass double dot should equal to g sine theta over 1 plus I center of mass over m a squared. Okay, so that is now gives the correct. This is acceleration, this is acceleration, this is dimensionless because I center of mass has dimension. Okay, so that is the correct one. Sorry. So it should be connected like 1 plus m a squared. Okay. For example, if this is disk, then we know that I center of mass is 1/2 m a squared. So it gives 1 plus 1/2 gives you 3/2. So it's 2/3 g sine theta for a disk. Okay. Now, so far we have done the computation with respect to the center of mass, but of course it should give you the same acceleration if you calculate it with respect to any point. So let's do this computation around O prime here now, because here also you can use dt over dl is equal to omega. Okay. Now, if you calculate the torque with respect to this point here, okay, so what is the torque with respect to that point here? So here, Fn, and here was Fp. So these two Fn and Fo does not contribute to torque because that has the same starting point. Here you have mg here. Okay, so this is A, so this is theta. So the torque around this point is what? This is torque is R cross F. Okay, so you have A torque around this point is A times F times sine theta. Okay, so that gives you A mg sine theta. Okay, so this one. So you can just think of this distance here, this distance, that is moment of arm, is A sine theta. Okay, so NO prime is mga sine theta, and you can still use this equation I explained for this laminar motion. So L is now going to be the center of mass moment of inertia is 1/2, and that is A. So therefore you have I, which is equal to 3/2 ma squared times theta omega dot. Okay, so that is the momentum around this point here, and also for the rolls without slipping, you can use x center of mass is equal to a phi dot. Okay, so you have this and this equation. So dt over dl is equal to, dt over dl is 2/3 ma squared times omega dot, which is equal to 3/2 m a square. Omega dot is what? Omega dot is a of x center of mass double dot, because this is omega, should equal to a mg sine theta. Okay, and that gives you x center of mass double dot should equal to what? M cancels, and this 3/2 gives you 2/3 a squared, a cancels, and g sine theta. Okay, which is this one, which is this one. So even if you calculate this motion with respect to this point, okay, the results are obviously the same. Of course, it should be. And this I just did it for the disk, but for sphere or arbitrary rigid body, the result must be the same. This one is just done for the disk. So I will just leave it as an exercise to verify that for an arbitrary I, that the result of calculation with respect to O or with respect to O prime are the same. Okay, so I urge you to go through this exercise.